Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the semester 2 final exam. So it's going to be on statistics, probability, as well as quadratics and parabolas. So let's get stuck into it firstly with statistics. So we start off by looking at box plot. So box plot is a statistical display. And what it displays is the 5-number summary of the data. So the 5 numbers in the 5-number summary, we have Q0, which is the minimum, Q1 the first quartile, Q2 is the median, and Q3 the third quartile. Finally, Q4 is the maximum. So box plots are also known as box and whisker plots because this thing here and this thing here, they are known as whiskers. So the whisker starts at Q0. So for this data, Q0, the minimum is 0. The box starts at Q1. So here that's 1. The median is that vertical line in the middle of the box. So the median is here. The median of this data is 2. And note, you calculate the median the same way you've calculated it since year 7. So Q2 is here, somewhere in the box. So Q3, the third quartile, is where the box ends on the right-hand side. So Q3 of this data is 4. So Q4, the maximum, well, that's pretty straightforward, except in this case, we actually have our maximum outside of the box plot. So normally this would be the maximum, but we've put an observation outside of the box plot. 9 is the maximum. The reason that we did that is because it turns out that this score here will be an outlier, and we'll go through exactly what that means in a second. So the box plot is also kind of dividing up the data into quarters. So 25% of the scores are between Q0 and Q1. So in this data, a quarter of all scores were between 0 and 1. There's also 25% of scores between Q1 and Q2. So in this data, a quarter of scores between 1 and 2. There were a quarter of scores between 2 and 4. And a quarter of scores above Q3. So Q0, Q2, and Q4, they're not new concepts, minimum, maximum, and median. The new concepts are Q1 and Q3. So you can see Q1 here is the point at which there are 25% of scores below it. Q3 is the point at which there are 25% of scores above it. So Q1 and Q3 are helpful. We need them to calculate what's known as the interquartile range, or IQR. So that's just Q3 minus Q1. So in this data, Q3 is 4 and Q1 is 1. So the interquartile range is 3. So the interquartile range is helpful because it's a better measure of spread than the normal range. So the range, which you've been calculating since year 7, would be 9 minus 0, which is 9. But this score out here is sort of on its own. It isn't a good indication of what the data actually is. Q3, the interquartile range, is Q3 minus Q1. So it's the range of 50% of the scores. It doesn't include outliers, so it's considered a more reliable measure of spread than the normal range is. So interquartile range is Q3 minus Q1. So let's look more at this score over here. So the maximum score here was 9, and it's an outlier. As I said, normally the maximum would be here where the whisker ends, but when there's an outlier, sometimes we put them outside the box plots because they're so different from the rest of the scores. Now, you've come across outliers for the last few years, but you were just looking and saying, oh yeah, that score is very large or very small, it must be an outlier. Now we have a definitive way to tell whether or not a score is an outlier. So the reason 9 is an outlier, well, let's look at what Q3 is. So Q3 here is 4. The interquartile range is 3. So in this data set, a score would be an outlier if it was greater than Q3 plus 1.5 times the interquartile range that we calculated here. So 4 plus 1.5 times 3 is 8.5. What that means is, in this data set, any score above 8.5 is considered an outlier. And that, of course, means that 9, this score here, is considered an outlier. In this data set as well, we'd consider an outlier anything that was less than Q1, which was 1, minus 1.5 times 3. So that gives you minus 3.5. So in this data set, we would consider a score to be an outlier if it was more than 8.5 or less than minus 3.5. We don't have any scores below 0, so there are no scores that are an outlier because of this. But there is, as I said, one score above 8.5, and therefore there is one outlier. And we usually leave outliers outside the box plot. So just note, box plots do not allow you to calculate the mean because we can't get from this how many scores there are or what the scores add up to. There is no way of telling the mean from this. All right, now we're going to go through an example where we actually construct a box plot. So I have a set of data here and I'm going to draw a box plot for it. So what you need to do to draw the box plot is find the 5-number summary. So I'm going to calculate each of these 5 things: the minimum, first quartile, median, third quartile, and the maximum. So let's start with the minimum because that's really easy. The scores are in order, so the minimum's clearly 72. The maximum's clearly 100. That's easy as. Now to find the median, note here that there are 9 scores, so the middle score is the median. Just as you calculated it in Year 7, the median is 78. Now this is how you calculate Q1 and Q3. To calculate Q1, it's the median of the lower half. So what we need to do is divide this data into half into 2 equal groups. Now there are 9 scores. So what we do is we now cross out the median. This is our lower half and this is our upper half. The median of the lower half is Q1. So the median would be halfway between these 2 scores at 75. That would be Q1. So for our data here, Q1, the median of the lower group is 75. And similarly, the median of the upper half would be halfway between 85 and 89, which is 87. So Q3 is equal to 87. It's as easy as that. Now, just before I construct the box plot, I'm going to check that there aren't any outliers. So a score will be an outlier if it's less than Q1 minus 1.5. Now we need to calculate the interquartile range. Remember, that's just Q3 minus Q1. So the interquartile range here is 12. So a score will be an outlier if it's less than 75 minus 1.5 times 12, and that means it's got to be less than 57. There are no scores less than 57. A score will also be an outlier if it's greater than Q3 plus 1.5 times the interquartile range. So that means it has to be greater than 105. Again, there are no scores less than 57 or greater than 105. There are no outliers, so all of these scores will be represented in the box plot. So let's go and graph it. So I've got Q0, which is my minimum, so I'd start my whisker here. Q1 at 75, so this is where the box starts, and then the median is at 78. Q3 is up at 87, which is about here, so this is where the box goes. And then I go all the way up to Q4, the maximum, which is at 100. So that is what the box plot looks like. Of course, yours will be drawn with a ruler and look much better. All right, now we're just going to quickly look at comparing the shape of box plots to histograms. So on your screen, I have 3 box plots, and we're going to draw what a corresponding histogram would look like. So let's look at the first one. So this one you can see there's a lot smaller distance on the left-hand side than the right-hand side, but this is supposed to still represent 25% of the data, the distance from here to here. Similarly, there's 25% of the data from Q1 to Q2. Q1 is where the box starts, Q2 the median is where the line is. And then there's 25% in this big range here and 25% in this range here. So what that will mean is there must be scores clustered here at the minimum, because this small distance contains as many scores as the distance from here to here. So if I were to draw a histogram, it would look like this. I can't tell its shape exactly, but it would roughly look like this. It would have a higher frequency of scores, higher bars closest to the minimum. Remember, histograms always have F frequency, how many times the scores occur on the y-axis, and the scores X on the x-axis. So this data is what we call positively skewed. It means that scores are clustered around the minimum, and we said that they're clustered around the minimum because there are so many scores in this small range, as many scores in this range as there are from here to here. So the next one, you can see that the box plot looks roughly symmetrical. So the histogram that corresponds to it would be symmetrical. So if I have frequency and score, the histogram would look symmetrical, and there would be higher bars you'd expect in the middle. So symmetrical box plots are easy to tell. As the name suggests, they have a symmetry. It's like the same from on left side as it is on the right side. So if we look at the final one, the third one down here, well, it's sort of the opposite of what happened in the first one. There is still 25% of scores between here, Q0, the minimum, and Q1, the first quartile. There's also 25% of scores in this range, but there's the same number of scores from here to here as there is from here to here, because Q2 to Q3 also represents 25% of scores. So this will be the opposite of the first one, and you will get a histogram that might look something like this. Scores will be clustered towards the maximum for the opposite reasons than in the first one. So if there's a small or much smaller distance from the median to the maximum, as there is here, median to maximum, lot smaller distance than from minimum to median, we expect that that data is negatively skewed. That again means that scores are clustered towards the maximum. So just make sure you're careful with skewness. It sort of goes in the opposite way that you'd expect. You'd think positively skewed would mean more high scores, but it means more low scores, and negatively skewed means higher frequency of higher scores. All right, let's now turn our attention to scatter plots. So scatter plots look like this. They don't have bars, they're not histograms. So scatter plots, what they require is two numerical variables. And what we're looking at is there a relationship between the two variables? So let's look at the first one. This axis, the y-axis, that would contain one variable, one numerical variable, and the other one would be plotted on the x-axis. They can be whatever you want. You know, this might be height, and this might be a student's weight. And each of these dots in the plane represents one observation. It has a value for the first variable and a value for the second variable. So if this was height by weight, this distance here would be like the weight, and this distance here would tell you the height. So we need to be able to look at scatter plots and determine the relationship. So we're looking at, firstly, whether the relationship is linear, whether or not you can basically draw a line through it. Now, this first one on the left-hand side with the blue dots, it's not perfect, but we'd say it's linear. It generally looks like you could draw a line through them. It's not a strong linear relationship, but you could generally draw a line through it. So this relationship in the first one is positive. So what it means is if I drew a line, the gradient would be positive. So if I drew a line through that, it leans to the right, its gradient is positive. It also means that as one variable, as the x variable, this variable is increasing, the y variable is generally increasing. So as I'm going across to the right, the scores are generally going up. So what this could represent, I'm just giving you an example, temperature versus ice cream sales. You'd expect that as the temperature increases, you'd sell more ice cream. It doesn't mean the relationship's perfect. You know, if you went to like Goodberry's in the middle of winter, sometimes it's really busy. What it's saying is, in general, we expect that as the temperature increases, so too ice cream sales generally increase. So let's look at this second one here. So this is a strong linear relationship because the data almost perfectly lies in a straight line. But this relationship is negative. That's because if I drew a line through the data, it leans to the left and has a negative gradient. Alternatively, what's happening is one variable is going up. As x is increasing along here, y is actually going down. So y starts off high, but as we go across, we're going down. So as one variable increases, the other decreases. That's what a negative relationship is. So an example of what this data might represent, the hours spent on Facebook and the test mark. You might expect that somebody who spends more hours on Facebook would not get as high a test mark. Again, it doesn't have to be perfect. It doesn't necessarily mean if you spend more time on Facebook, you absolutely will get a worse test mark. It just means generally as hours on Facebook increases, test mark decreases. So let's look at this final one here. So this one has no linear relationship. It sort of looks like the points are at random. As x is increasing, y is neither increasing nor decreasing. It's just kind of all over the place. So as an example of a scatter plot that might show no relationship, I've chosen test mark versus shoe size. You wouldn't expect that one affects the other at all. You wouldn't expect that as you have a higher shoe size, you get a better test mark. There's no reason at all that the two would be linked. So that's how to look at scatter plots and determine the relationship. Let's now look at making a scatter plot. So what we have here is a table of data, and we're going to calculate the line of best fit. So this table here gives you heaps of values for the minimum temperature and the maximum temperature. So each observation is like a day with its minimum and its maximum temperature. So I have actually plotted most of these scores. For example, you can see 0, 20, this score here. I just plot x as 0. And then go up to y is 20. For 5, 19, I start at 5 for x and go up to y equals 19. So the last one I have to plot is this last one, 4, 16. So I've now plotted that information here. Of course, it's just like plotting points in the Cartesian plane that you know how to do already. So we're going to first draw a line of best fit. So what I want is I want the line to go through at least 2 points so I can calculate its equation, and I want there to be the same number of points above and below the line. So hopefully you see I can draw this blue line that I've shown you there. It goes through 2 of the points so I can calculate its equation, and you can see that there are 3 points above the line and 3 points below the line. So we're going to calculate the equation of this line of best fit. So this line goes through 317 and 622. So we're calculating the equation of a line that goes through 317 and 622. So remember the way we did it, the same way we did it in term 1. You first calculate the gradient. So using this formula. So we say that this is y1, y coordinate of the first, x coordinate of the first, and so on. So using this formula, we get y2 minus y1 over x2 minus x1. So the gradient is 5 over 3. The next thing you need to do is calculate the y-intercept, where it would hit the y-axis. So remember, the equation of any line is y equals mx plus b. What we're going to do is we're going to substitute the gradient that we just found, which is 5 over 3, and we substitute x and y from a point that goes through, that the line goes through. So we can either use this point or this point. It doesn't matter. I'll just use this point here. So what I'm going to do is change y to 22, and the x value of that point was 6. So I'm going to rub out x and change it to 6. Now I just solve this equation for b. So 5 over 3 times 6 is actually 10. So b is just 12. The equation of the line of best fit is y equals gradient times x plus y-intercept. So I'm going to rub out the working out of how I calculated that line so I can do a few more questions. Please pause and copy this down if you need. So now that we've calculated the equation of the line of best fit, we can use it to predict value. So if I've given a certain x value, so I tell you the minimum temp 7 or 15, I can predict what the maximum temperature will be. So that's really simple. If x is 7, according to my line of best fit, y is just 5 over 3 times 7 plus 12. If you put that on your calculator to 2 decimal places, you get like 23.67. So now if x was 15, my line is saying that y is 5 over 3 times 15 plus 12. So my line predicts if the minimum temperature was 15, I just substitute minimum temperature for x, because minimum temperature is x, and 5 over 3 times 15 plus 12 gives me 37. So the thing about this is, this one is reliable. The reason it's reliable is because 7 was within the range of values I had. I had a range of values for x from 0 to 8. 7's within that range, so this is a reliable estimate. This one here is not reliable. The reason is because 15 was not in the range of values I had for x. So if I substitute x for a value outside that range, it's not considered reliable anymore. And that makes sense because we don't know what's going to happen over here when x is 15. This line may not be the line of best fit anymore. So only values within the range we were given can we use to make a reliable estimate. All right, now we're going to move on to probability. So let's start off probability by looking at a question like this you should have encountered many times. So, class of 30 students, we have 7 with blue eyes, 5 with blonde hair, 21 have neither blonde hair nor blue eyes. So what I'm first going to do is put this information in a Venn diagram and two-way table. So you should know by now Venn diagrams, we have a rectangle and we have two circles representing sets. So I'm going to let A be the set of students with blue eyes and B the set of students with blonde hair. The reason this is a Venn diagram or two-way table problem is because there are two sets. Blue eyes, one set, blonde hair, another set, and students can be in one, both, neither, whatever. So let's fill in the Venn diagram with 4 numbers. We need the 4 numbers in these 4 boxes. So you might be sitting there thinking, how does this add up? 7 plus 5 plus 21 is equal to 33, but there are only 30 students. How does that work? Well, the only way that works is if we've double counted 3. That means that we've counted 3 students in the blue eyes and the blonde hair. However many you've overcounted goes in the middle, so there must be 3 students in the middle. So let's look at the rest of this A circle here. So this is the blue eyes circle, and I need to have 7 students in that circle. I already have 3 inside the circle. They're still in the A circle. So what I need is 4 more to go here. Similarly for the B circle, I've already got 3, and I'm supposed to have 5 with blonde hair. So I need another 2. And the 21 that have neither, they go outside the circle here. So note the 4 numbers in these boxes, 21 plus 2 plus 3 plus 4 does equal 30. So I know I've done the right thing. Let's now put this information in a two-way table. So two-way tables are just another way to represent the same information as in a Venn diagram. So the 2 ways, we have A or A dash means not A. That's one way. And the other way, we have B or not B. So two-way tables, unlike Venn diagrams, have a row and a column in which we put the total. So these 4 numbers that occur in the Venn diagram are the same 4 numbers that will go in here. So let's look at this cell here. That's A and B. So we can see from the Venn diagram there were 3 students in the A circle and the B circle. So this cell here is B and not A. So there were 2 students in the B circle and not the A circle. Similarly, we have 4 that go here. There were 4 in the A circle but not the B circle. And this last one here, because it's in this row, it's not B and not A. It's in neither circle, and that's those 21 there. So these 4 numbers correspond to the 4 numbers in the Venn diagram, and we can just add up the totals. So once again, we've got everything adding up to 30, which is what we wanted. So what we have to do is we have to know what A and B, A or B mean. So this here, this little symbol means and or intersection. A intersection B, or as we usually read it, A and B. So that corresponds to the middle of the Venn diagram. So in the question we're talking people who have blonde hair and blue eyes. So that's A and B. And in the two-way table, it's this cell here that are in A and B. So if I was asked to find the probability of A and B, that would just be 3 out of 30. So that's saying if I picked a student at random, the probability they have both blonde hair and blue eyes is 3 over 30, or 0.1. So the opposite of that kind of thing is A or B. So this U means or union. So if we're talking about unions, now we're talking about everything that's in A or B or both. So that would actually include the middle here, but also includes everything in both circles. So in the context of this question, A or B is everyone who has blonde hair, everyone who has blue eyes, or those that have both. So if we look at the two-way table, it's actually including these 3 cells here. It's everything but what's outside the circle in the Venn diagrams. It's everything but this cell here. Because the people in this cell, they have blue eyes, so they're included. The people in this cell have blonde hair, so they're included. And the people here have both, so they're included. So if I was asked to find the probability of A or B, that would be the probability if I pick someone at random, they either have blue eyes, blonde hair, or both. It would be 4 plus 3 plus 2. There are actually 9 out of 30 that have blonde hair or blue eyes. And that simplifies to 3 out of 10. So make sure you understand the difference. We're going to do more work on that. Another thing I want to go through is this here. This actually means A given B. This is conditional probability. So why do we call this conditional? If I'm talking about A given B, I'm saying the condition that B has happened. So in this question, if I'm calculating the probability of A given B, I'm saying I know that the person has blonde hair. I know that B has happened. What's the probability A also happens? So I'm saying I know that I've picked someone at random, but they have blonde hair. I know they have blonde hair. What's the problem? That blonde-haired person also has blue eyes. So if we look at our Venn diagram, we can see that if I picked someone with blonde hair, there are 5 choices, 3 plus 2. And of those 5 choices, 3 of them have blue eyes. So I expect the probability to just be 3 over 5. So there is a formula for probability of A given B. It's probability of A and B over probability of B. So whichever one's listed second in the given statement, the conditional statement, is what goes on the bottom. So I could use that formula here as well to calculate the probability. The probability of A and B, I actually figured that out. That was 3 over 30. And then the probability of B, well, that's the probability that someone has blonde hair. That's 5 over 30. And that, 3 over 30 over 5 over 30, just gives me 3 over 5. So again, probability of A given B says I know B's happened. What's the probability A also happens? So now we're going to look a bit more at A and B and A or B. So on your screens at the top here is a formula for calculating probability of A or B. You just add their respective probabilities and then subtract the probability that they both occur. Now, sometimes this thing here, probability of A and B, will be 0. If that's the case, we say A and B are mutually exclusive. So mutually exclusive events are events that cannot happen at the same time. So for example, you getting an A in maths, you getting a B in maths. They're mutually exclusive. You can't have both. You can't get an A and a B. So if two events are mutually exclusive, which means they can't both happen, then this formula up here, we can just leave this off. Probability of A or B is just the sum of the two probabilities. So the general rule here is or. If you're doing an or question, you have to add probabilities. So let's look at a couple of quick examples to hopefully make this clearer. Let's have a go at these two questions here. A card is picked from a normal deck of 52. What's the probability the card is a 2 or 3, an ace or a diamond? So looking at this first one, note this word or. So we're using the or rule straight away. We should be adding some probabilities. Now, the events 2 and 3 are mutually exclusive. You can't pick a card that's both a 2 and a 3. So the probability of a 2 or a 3, because they're mutually exclusive, I can just find the probability of each of them and then add them together. So the probability I get a 2, there are 4 2s out of 52 in the deck, and there are also 4 3s out of 52 in the deck. So the probability I have is just 8 over 52, and that simplifies to 2 over 13. So when they're mutually exclusive, just add together their respective probabilities. Now let's look at the second one. So we've got an ace or a diamond. This is another or question. These, however, are not mutually exclusive. You can get a card that is an ace and a diamond. That would be the ace of diamonds. So the probability I get an ace or a diamond, I can still add together their probabilities, ace plus diamond, but I need to subtract the probability that I get both of them. So the probability of getting an ace is 4 out of 52, because there are 4 aces out of 52 in the deck. The probability of getting a diamond is 1 over 4, because there are 4 suits: hearts, diamonds, spades, and clubs. The probability I get an ace and a diamond is 1 out of 52. There is one card in the deck that's an ace and a diamond. It's the ace of diamonds. So if we add up all of this, we get 16 over 52, which simplifies to 4 over 13. So in this second one, we had to use this rule because they were not mutually exclusive. I can get an ace and a diamond. In the first one, we could just use this simplified version of the rule here because they were mutually exclusive. Just looked at an or rule, we're now going to look at an and rule. So to understand the and rule, we need to know what independence means. So we say two events A and B are independent if the probability of one does not affect the probability of the other. So for example, each time you toss a coin, the result is independent of the previous time that you tossed a coin. If you got a heads last time you tossed a coin, it doesn't affect your chance of getting heads or tails the next time you toss a coin. So only in the case that they're independent, the probability of A and B is just the product of the probabilities. You just multiply their probabilities together. This is actually the same as saying that probability of A given B equals probability of A. All of this stuff is true when and only when the events are independent. So just as when we're doing an or question, we should think about adding. When you're doing an and question, we should think about multiplying. So let's look at a few examples. So first question, I toss 4 coins in a row. What is the probability I get all 4 heads? So as I just said, each time you toss a coin, the event is independent of the previous. So the probability you get heads the first go is a half. The probability you get heads the second go is a half. The probability you get heads the third go is a half. and the probability you get heads the fourth go, you guessed it, is a half. Because each toss is independent of the last toss, we can multiply these probabilities together. The probability I get ahead the first go, and the second go, and the third go, and the fourth go is just the product of all of their probabilities, so it's just 1 over 16. So in the second question, we're not actually using this rule up here. We're just going to use this rule to check independence. So I pick a card randomly from a deck. What's the probability it is a 4 given that it is red? This means conditional probability, the given statement. We're then going to decide whether or not these two events are independent by using this rule here. So remember, the formula for a conditional probability was this. So the probability of A given B is the probability they both happen over the probability the second one happens. Whichever one's second goes on the bottom. So the probability I pick a card that's 4 and red. Well, there are 2 red 4s in the deck out of 52. The probability I get a red card is a half, because you can get, of course, black or red. They're equally likely. So that actually gives me 1 over 13, right? That's the probability of saying, I know I picked a red card, what's the probability it's a 4? It's 1 over 13. But the probability of just picking a 4, regardless of whether it's red or black, well, there are 4 4s in the deck out of 52. It's also 1 out of 13. So because the probability of 4 is the same as 4 given red, these two are independent, because probability of A given B equals probability of A. And this highlights what independence means. The probability of getting a 4, given it was red, it didn't change the probability. It was just the probability I pick a 4 normally. And that's what this formula is saying. Two events are independent if the probability of A doesn't change, given that something else B has happened. B hasn't affected the probability of A. So now we're just going to do a couple of quick examples involving both and or. So here we're told that A and B are independent. Probability A 0.6, probability B 0.3. We're going to calculate probability of A or B. So remember, we know that probability of A or B, to find that, you add up the respective probabilities and you minus the probability they both happen. So in this case, we're not told A and B are mutually exclusive. They can't be if they're independent. We're just told they're independent. So that means that probability of A and B, this one here, will be those two multiplied together. So probability of A plus probability of B minus the probability of A and B. We can multiply them together because A and B are independent, and you just get 0.72, and we're done. Let's have a go at this question here. So James bets in 2 horse races. The first has 12 contenders. The second has 11 contenders. He wins a prize if he picks the winner. What is the probability that he wins at least one prize, assuming that each horse is equally likely to win? So this involves both independent events and mutually exclusive events. So we're actually asking, what is the probability that he wins both? Because that's at least one prize, or he wins the first one only and loses the second one, or he loses in the first one and wins the second one. So each of these 3 events, 1, 2, 3, is mutually exclusive. You can't have more than one of these. You can't win both races and only win the first one. You can't win only the first one and then win only the second one. So they're mutually exclusive. So we're going to add up their respective probabilities. So now we have to calculate each of their respective probabilities. So let's start by calculating the probability he wins at both races. Well, this involves independent events because the probability he wins at the first one doesn't affect the probability he'll win at the second one. The probability he wins at the first is 1 over 12 and wins at the second is 1 over 11. Now we calculate this one. Probability he wins at the first one is again 1 over 12. The probability he loses at the second one is 10 over 11, because there are 10 ways he can lose. And then similarly for the last one, this one here, the probability he loses the first one is 11 over 12. Probability he wins the second is 1 over 11. I'm multiplying in each of these cases because of independence. Losing the first race doesn't affect his chance of winning the next race. As I said, because each of these three events is mutually exclusive, I add up their respective probabilities. So if I add all these up, and you can use your calculator, just get 22 over 132, and you can simplify that to 1 over 6. And there we have it. We are done. All right, the last thing we need to do in probability is tree diagrams. So let's say Ben has won a prize for being a great student. He randomly picks a prize from a bag containing 4 gift vouchers, 3 phones, 2 watches. He selects 2 prizes, one after the other, and what's the probability that he gets a watch? So we're going to represent the possible outcomes in a tree diagram. That's what tree diagrams do. They list all the possible outcomes. So they are for multi-stage events, events that occur in stages. This occurs in stage because he's going to pick a first prize, that's the first stage, and then a second prize, that's the second stage. So what we do is we line up our columns for the stages. So the first stage, he can pick a gift voucher, a phone, or a watch, and second go, he can pick a gift voucher, phone, or watch. Gift voucher, phone, or watch, and so on. We usually draw branches as well, and that's why it's called a tree diagram or a probability tree. Now, there'd be no point doing it if we don't list the outcomes. So we have to list all the possible outcomes. He can get 2 gift vouchers, a gift voucher and a phone, a gift voucher and a watch, and so on. So here is the list of all the outcomes. Now notice each of these outcomes is not equally likely, because you are more likely to get a gift voucher than get a phone, you're more likely to get a phone than a watch. So what we have to do is write the probabilities on the branches. So when he's first picking, there are 4 plus 3 plus 2, there are 9 prizes, 4 gift vouchers, so he has a 4 out of 9 chance of getting a gift voucher, 3 out of 9 or a third of a phone, and 2 out of 9 for a watch. Now, we also have to calculate the probabilities on these second branches. So that will actually be determined by whether or not this experiment is with replacement or without replacement. So let's first do this with replacement. So with replacement means after Ben has picked the first prize, we replace it with something identical to what he picked. So that means if he picked the gift voucher the first go, we put another gift voucher in, so there are still 4 gift vouchers and still 9 prizes. It means the probabilities do not change on the second go. So to calculate the probability of each of these outcomes, what you do is you multiply the branches. So the probability of GG is 4 over 9 times 4 over 9. But to save ourselves some time, let's circle which ones we're interested in. We want the probability he picks a watch, so we're interested in this one, and all of these 3. So let's only calculate these probabilities. So starting here, the probability of a gift voucher then a watch, I multiply the probabilities together. So it's 4 over 9 times 2 over 9, which gives us 8 out of 81. So similarly for this one here, the probability of a phone then a watch, it's 3 over 9 times 2 over 9. That just gives us 6 over 81. And we do similarly for these 3 events down here. So we're interested in the probability that this, or this, or this, or this, or this happens. Each of these is mutually exclusive. You can't get GW and get, say, WW. So I can just add together all of these numbers here. So if I add all of these 5 numbers, I get 32 out of 81. That is my final answer, the probability that he gets a watch. So now what would happen if I change this? So instead of being with replacement, it was without replacement. So this means after he's picked the first prize, it's not replaced. So let's say he got a gift voucher. It is not replaced. There'd only be 3 gift vouchers left and 8 prizes left. So the only thing that would really change about our tree diagram, all these outcomes would stay the same, but these probabilities would change. So if I picked a gift voucher first go, there'd be 3 left out of 8. But the first go, I didn't pick a phone, so there'd still be 3 phones and 8 prizes. There'd still be 2 watches and 8 prizes. So I'm going to go down and fix up all of these probabilities. That's the only thing that really changes about the tree diagram. So now each of these probabilities has changed. So that means I need to recalculate the probabilities of each of these 5 events. So to calculate each probability, the probability of this event, for example, I'm going to do the same thing I did before. I'm going to multiply together the 2 probabilities. It's just that the numbers are slightly different. So this one will be 4 over 9. Now I'm timesing it by 2 over 8, which gives me 1 over 9. And I'm going to do similarly for each of these 4 events. So I've done exactly the same thing. The numbers are just slightly different, but the probability he picks a watch is this one, plus this one, plus this one, plus this one, plus this one. They are once again mutually exclusive events. So adding up each of those 5 probabilities gives us, this time, 15 over 36, which simplifies to 5 over 12. So when it was with replacement, the probability of getting a watch was 32 out of 81, which is about 0.4. Now, when it's without replacement, it's 5 over 12, which is closer to 0.42. So the probability of him getting a watch has gone up slightly, and that's because the probability of things like getting 2 gift vouchers or 2 phones has gone down slightly. All right, that's all for probability. Now we move on to quadratics. So we're going to start off quadratics by doing expansions. The first one's not even a binomial expansion, but you just times 2x by x, 2x by minus 5 using the distributive law. So 2x times x, 2x times minus 5, and you're done. We've got a quadratic expression because of this x squared term. So let's do the second one. So what we can do is use the FOIL method. So we can do firsts, then O, outsides, x times 5, then insides, 3 times x, and then last, the thing that occurs last in both brackets. So if you simplify that, these are like terms. You get x squared plus 8x plus 15. Note there is a quick way to do it, and I'll show you in the next example. So the quick way, so this is when you have just x's in both. There's no number written in front of the x's. So you square the x to get x squared. The coefficient of x is these 2 added together. So minus 2 plus minus 9 gives you minus 11. That goes in front of the x. And the constant term is minus 2 times minus 9, which is positive 18. That's just a quick way. You can use either way, the FOIL, if you want as well. So the next one is difference of 2 squares. Once again, I can use FOIL. I can go firsts, the thing first in each brackets, outsides, insides. This will be minus 3 times x, and then lasts, minus 3 times minus 3. So there are once again like terms. 3x plus negative 3x is 0. Those 2 cancel each other out, and I'm left with x squared minus 9. So the quick way to do these ones, so this is where you have the same thing in each bracket, but one's a plus, one's a minus. It's the difference of 2 squares. All you do is square the first, so 2x all squared gives you 4x squared. Square the second, and stick a minus between them. Just might save you a bit of time other than doing FOIL. So for perfect squares, you can again use FOIL if you want. Remember, squaring something means times it by itself. So firsts, outsides, insides, and then lasts. Minus 5 times minus 5 is positive 25, and once again we need to collect like terms. Minus 5x gives you minus 10x. So the quick way to do a perfect square, square the first and square the second. Most people think this is just x squared plus 4. Please don't make that mistake. When you are doing a perfect square, there is always a middle term. It's not just x squared plus 4, there is a middle term. That middle term is 2 times x. 2 times the product of the two things in the bracket. So 2 times 2 is 4, times x is 4x. So this will be plus 4x plus 4. All right, let's now go on to solving quadratic equations. So we're going to solve each of these equations. These are quadratic equations because of the x squared term. So what we want to do is factorize and use the null factor law. So just be aware that these first three here are binomials because they have two terms, and all of these are trinomials. The way that we do the first step of factorizing is slightly different whether we have a binomial or a trinomial. So let's look at the first one. So when we're doing binomials, there's two methods. There is highest common factor or difference of two squares. So these two here have a common factor. Both terms have an x in them. Also 6 and 9 have a common factor of 3. So what we do is we take out the highest common factor. What do I times by 3x to get the first term, 6x squared? So I need to times by 2x. What do I times by 3x to get negative 9x, the second term? And that's minus 3. So we factorized. Now, the null factor law says that when you have something times something equal to 0, either the first thing equals 0 or the second thing is equal to 0. So in this case, either 3x is equal to 0, that means x is equal to 0. That's one solution. The other solution is if the bracket equals 0. If 2x minus 3 is equal to 0, you can just solve that like a linear equation. 2x minus 3 equals 0, 2x equals 3, x equals 3 over 2. So the two solutions here are x equals 0 and x equals 3 over 2. So let's look at the second one. There is no common factor with x squared in 25. This is a perfect square minus a perfect square. So to solve it, please factorize. What people have been trying to do in previous tests, they add the 25, but they only get one solution, x equals 5. Please don't do that. Don't treat this like a linear equation and add 25 to both sides, because people always miss a solution. What we want to do is factorize and then use the null factor law. So to factorize the difference of two squares, get two brackets, square root the first, so square root of x squared is x, square root the second, one bracket gets a plus, one gets a minus, doesn't matter which one. So either x plus 5 is equal to 0, that means x is minus 5, and the other solution is if x minus 5 equals 0, then x is plus 5. So there are two solutions, 5 and minus 5. If you treat it like a linear equation, then you might only get one solution. So this third one is a binomial. So this one, there is a common factor. The common factor is 3, because 3 goes into 3, 3 goes into 12. So if we take out the common factor, we're left with something in brackets that is the difference of two squares. So I'm going to factorize this. So remember, what I'm going to do, I'll keep my 3, two brackets, square root the first, square root the second, one gets a plus, one gets a minus, and that's equal to 0 because of what the equation said. So the 3 doesn't matter. Either x plus 4 equals 0, x is minus 4, or the second bracket equals 0, which would mean x is plus 4. So the two solutions here are 4 or minus 4. All right, now we're going to look at trinomials. Do not, whatever you do, try and get, the 8 on one side and then divide by 6. You'll be there all day and you won't get anywhere. We're going to factorize and use null factor. So the way we factorize trinomials, we find two numbers that times to the constant and add to the number in front of x. So we want to find two numbers that add to 6 and times to 8. Well, that's just 4 and 2. So they go in the brackets like this, x plus 4 plus 2, because 4 and 2 multiply to 8 and add to 6. So that's equal to 0. So either the first thing equals 0, if x plus 4 equals 0, x is minus 4, or the second thing equals 0, and that would mean x is minus 2. So the two solutions here are minus 4 and minus 2. So let's look at the second. We're going to factorize the same way. Two numbers that multiply to 49 and add to negative 14, they're actually minus 7 and minus 7. So this one's x minus 7 squared is equal to 0. This one has only one solution. If the thing in brackets is equal to 0, that means x is equal to 7. That's our only solution. So the next one's a bit harder because the constant term's negative, but we're still going to do the same thing. Find two numbers that times to negative 30 and add to negative 1, because if it's not written, then the coefficient of x is 1. So two numbers that multiply to negative 30 and add to negative 1, it turns out those numbers are minus 6 and positive 5. So the two solutions, x can be positive 6, that would make this bracket equal 0, or x can be negative 5, because that would make this bracket equal to 0, and we're done. So let's look at this final one here. So to use the null factor law, one side has to equal 0. If it doesn't, don't stress, we'll make it equal to 0. What we're going to do is we're going to first subtract 4 from both sides. We get x squared minus 4 is negative 5x. Then I'm going to add 5x to both sides, because what I want to do is get one side equal to 0. When I have one side equal to 0, I don't treat it like a linear equation. Now, if I want to factorize this, I'll run into trouble. There are not two numbers, or it's not easy to find, two numbers that multiply to negative 4 and add to 5. So when that happens and you're solving an equation, if you can't factorize, use the quadratic formula. So remember, this is the quadratic formula. Yes, it'll be given to you in the test. So we usually start by calculating the discriminant, this part here. So remember, b is the coefficient of x, a is the coefficient of x squared, c is the constant term. So in this case, the discriminant, b squared minus 4ac, so it's b squared minus 4 times a times c, gives us 41. Since the discriminant's positive, there will be two solutions. So those solutions will be x is minus b plus square root of discriminant over 2 times a, 2 times 1 is 2, or minus b minus square root of discriminant over 2. They are the two solutions. All right, we're just going to do one challenge question of quadratics and then move on to parabolas. So the equation x squared plus kx plus 16 equals 0 has no solution. We're going to find possible values for k. So no solutions means the discriminant b squared minus 4ac must be less than 0. So in this case, b, the coefficient in front of x is k. So we have k minus 4 by a is 1. Number in front of x squared is 1. By c, which is 16, must be less than 0. So we get k squared minus 64 is less than 0. And you know how to solve inequalities. They're very similar to linear equations. So if k squared is less than 64, we must have that k is less than 8. And that makes sense, because if k was like 9, k squared would be 81, so it'd be more than 64. But we also need at the same time that k is greater than minus 8. Because if k was minus 10, for example, k squared would be 100, which is clearly not less than 64. So we must have that k must be between minus 8 and positive 8. It can take any value between, but not including minus 8 and 8. So it can be like 1, 2, 3, whatever. When it says possible values, we need to give all possible values, and this statement does that. All right, the last thing we will do is turning quadratic equations into a graph, so we'll graph a parabola. So we're now going to graph the parabola y equals x squared minus 2x minus 15. So when graphing a parabola, you need to find each of these 4 features. So you find the orientation. If the coefficient of x squared is positive, it's a smiley face. If the coefficient of x squared is negative, it's a frowning face. You find the y-intercept by letting x equal 0. There's always one and only one y-intercept. You find the x-intercepts by letting y equal 0, so there might be 0, 1, or 2 x-intercepts. And then finally, you find the turning point axis of symmetry using this formula. So this is the equation of the axis of symmetry. It's also the x value of the turning point. Remember, the line of the axis of symmetry, always a vertical line, always goes through the turning point. When you found the x value of the turning point, using this formula, you substitute into the original equation to find the value of y. So let's go and do all of these for the parabola y equals x squared minus 2x minus 15. So, firstly, its orientation will be a smiley face because the number in front of x squared, not written, it is positive 1. Positive means smiley face. Secondly, so the y-intercept, if I let x equal 0, it'll just be 0 minus 15. The constant term gives us the y-intercept. So y-intercept is going to be 0 minus 15. So to find the x-intercepts, I let y equal 0. So now I've got a quadratic that I need to solve. So this is a trinomial. I'm going to find two numbers that multiply to this and add to this. So they turn out to be minus 5 and positive 3. So the two solutions to this are x equals 5, positive 5, or negative 3. They are the two x-intercepts. So then for the fourth, we'll find x equals minus b over 2a. So it's minus b is minus 2 over 2a. So that's just equal to 1. So x equals 1 is the equation of the axis of symmetry. It's the x value of the turning point. When x equals 1, y equals x squared minus 2 times x minus 15 actually gives us minus 16. So the turning point is 1 minus 16. So let's draw a rough sketch of what that would look like. So I'm just drawing a rough sketch of what it looks like. So it'll go through these 2 points, the intercepts. We've got our y-intercept here at minus 15 and our turning point at 1 minus 16. So because I know it's a smiley face, I can just join these up. So what it will do, it will come down, go through the x-intercept, hit the y-intercept, and it goes to the turning point where it stops and turns around, and it'll go in the other direction and through the x-intercept. So should put arrows on and also label the equation. So how you graph any other parabola would be the same, just follow those 4 steps. All right, now we're just going to do challenge question involving parabolas, and then we're done. So we are going to work out the equation of each of the parabolas below. Now we're going to do these in a slightly different way. So the reason is, in the first one we know the turning point but not the x-intercepts, whereas in the second one we know the x-intercepts but not the turning point. So we have in the first one that the turning point is at 1, 2. So the parabola has been shifted 1 to the right and 2 up. So it will be of the form something times x minus 1 squared. Remember, x minus 1 shifts it 1 to the right. This number in the brackets determines whether it goes right or left. It goes in the opposite way that you'd expect. So negative means to the right. That means it's been shifted to the right 1 unit, and up 2 is plus 2. So when you're talking up or down, this number tells you whether you go up or down. It goes in the way that you'd expect. Positive up, negative down. So the only thing we need to do now is find a, because a could be really any number, except we expect it'll be negative because the parabola's a frowny face. So to find a, I'm going to substitute in another point. So I'm going to substitute in this point here, the y-intercept, x equals 0, y equals negative 1. So then I get negative 1 equals a times x minus 1 squared plus 2. Now, when doing these before, people seem to have real trouble with this. Order of operations, you do this first. So 0 minus 1 is minus 1 squared is 1. So now we subtract 2 from both sides, we get minus 3 is equal to a. So this equation will be y equals a, x minus 1 squared because it's been shifted right 1, plus 2 because it's been shifted up 2, and we're done. So in the second one, we are given the two x-intercepts. So it will be of the form y equals a x minus the first intercept, x minus the second intercept. And the reason it's like this is because if 3 is an intercept, we need an x minus 3. So when I substitute x for 3, y is 0. When I substitute x for 4, y is 0. That's what it means an x-intercept. When x is 3, y is 0. When x is 4, y is 0. That's why it has to be like this. Once again, we need to find what a is, and we can find a by substituting in the y-intercept, another point. So when y is equal to 12, we have x is equal to 0. So we have 0 minus 3 times 0 minus 4. So we can do these two multiplied first. Minus 3 times minus 4 is positive 12. So I get 12 equals 12a. A is equal to 1. So y is just equal to 1, x minus 3, x minus 4. I can expand that if I like, depending on what the question asks. So it would be x squared minus 7x plus 12. You can just expand with FOIL. So the way we find the equation of the parabola, we need at least 3 points, and we do it slightly differently depending on whether we're given the turning point or the x-intercepts. Alright, sorry for such a long video. Best of luck studying. You'll be fine. You're a superstar. I believe in you. Please ask if you have any questions. This has been the luckiest maths teacher in the world. Have a great day.